Next, we move to the last part of step growth polymerization topic, which is known as stoichiometric imbalance. Before we go into details about what stoichiometric imbalance, first let's understand the basic concept of stoichiometric. So stoichiometry is actually the calculation of products and reactants in a chemical reaction. It is basically concerned with numbers, and it's an important concept in chemistry that help us use balanced chemical equations to calculate amounts of reactants and also of products. In a polymerization, stoichiometric is largely relates to the molecular weight of the polymers produced. So we need to have a good stoichiometric balance to produce a polymer of very high molecular weight. So if your polymer have high molecular weight, so you have advantage on the strength of the polymer produced. But sometimes too much molecular weight is also very difficult especially during processing. So in some applications, sometimes it is necessary to limit the molecular weight. So if we want to reduce the molecular weight of the polymer produced, it is called as stoichiometric imbalance. So there are few examples of polymers that being polymerized that use stoichiometric imbalance that yield a polymer with low number of molecular weight. So one of the example is in the production of polyether, which is epoxy resin. So it only process to an oligomer stage. So oligomer is low number of polymer change, which is between only 2 to 8. So these small molecules of polymer are subsequently converted to a network polymer by appropriate reactions of terminal epoxide group. The other example is in the polymerization of unsaturated polyester, which is processed to moderately low molecular weight before being cross-linked. And last example we can see in the polymerization of polyamide, where molecular weight must be kept low because too high viscosity will affect the processing process. For example, during extrusion of filaments through the fine holes of a spinneret. So these are few examples on how you limit the molecular weight of few polymers. So we can say that there are few things that we can do during the polymerization to limit the growth of molecular weight in step growth polymerization. So first you can do is by quench cooling. Quench mean rapid cooling. So during the polymerization, when your polymer has achieved the desired molecular weight, you can stop the reaction by do rapid cooling when the desired molecular weight is attained. And number two, you can use an excess of one monomer when two difunctional monomers are polymerized. You have two different monomers, monomer A and monomer B. So to limit the growth of molecular weight, you can use excess of only one monomer. And lastly, use small amounts of monofunctional reactant. So these are the three ways that what you can do to limit the molecular weight. So these are the example of polymerization of different polymers that have utilized these three different ways to limit the growth of molecular weight. So to relate between the stoichiometric imbalance and degree of polymerization and also the reaction conversion, so we can write new expression by modify the characters equation. So we have the new factor R here, which is our stoichiometric imbalance. So the stoichiometric imbalance can be obtained by using this formula where R equal to initial of A functional group divided with initial B functional group. For stoichiometric imbalance less than 1, okay, you can determine the reaction conversion P, or you also can call extent of reaction. So the extent of reaction, the expression for extent of reaction P in relation to the stoichiometric imbalance can be calculated by using this formula, which is the extent of reaction equal to the initial functional group A minus functional group A divided with initial functional group A. Lastly, the number of molecular chain N of a stoichiometric imbalance polymerization can be calculated by using this formula, which is N equal to initial functional group A divided with 2 times 1 plus 1 over R minus 2P. Therefore, the total number of repeating units of initial monomer is given by this equation, which is initial number of repeating unit equal to half times initial functional group A plus initial functional group A divided with stoichiometric imbalance equal to the initial functional group of A divided with 2 times R plus 1 divided with R. Lastly, to write the expression for degree of polymerization with stoichiometric imbalance R, so we can say that if stoichiometry of imbalance is equal to 1, then degree of polymerization is equal to 1 over 1 minus P. This is the basic formula of degree of polymerization. So our final formula for degree of polymerization is when monomer is completely used up in the polymerization, that when P extent of reaction is equal to 1, the final equation for degree of polymerization becomes dP equal to 1 plus R and 1 minus R. So this is the final equation for degree of polymerization in terms of stoichiometric imbalance. However, if you use another monofunctional reagent to limit the molecular weight of the polymer produced, so you have to modify the definitions of stoichiometric imbalance R. So the imbalance factor R can be redefined as R equal to initial functional group A divided with initial functional group B plus 2 initial functional group B. So the factor 2 here, the number 2 here, is because each B molecule is equally as effective as one excess BB monomer in limiting the molecular weight. In a summary, okay, as a comparison with stoichiometric imbalance, there are few ways that can be done to achieve successful synthesis of high molecular weight step growth polymer. So there are few things that can be done to produce polymer with high molecular weight. The first one is by using high reaction rates. Okay, this can be done by removing byproduct to drive the reaction to high conversion. So this can be done by distillation under high vacuum or by azeotropic distillation. So this means that before you start the polymerization, all the chemicals, I mean the monomers, the catalyst, the medium, the solvent used in that particular polymerization need to be purified first by distillation to remove any byproduct present in that chemical, so that you can produce high purity polymers. Okay, the other thing that you can do is by using exact stoichiometric balance. So you know the difference, right? So the stoichiometric imbalance is to limit or to reduce the molecular weight of polymer. But if you want to produce high molecular weight polymer, it is called as stoichiometric balance. So stoichiometric balance can be done by control the monomer feed composition or use the equivalent of functional group of each monomers to produce molecular weight to produce high molecular weight of polymer. And lastly, to use the monomer purity to increase the purity of the monomer. This can be done by control the monomer purity in order to get high yield and carry out the polymerization under exclusion of oxygen. So your polymerization must be carried out in a closed reactor and away from any oxygen. Okay, normally during polymerization, we will let nitrogen gas to flow in to your reactor. Therefore, that polymerization is carried out under nitrogen environment without any oxygen. This is because oxygen can lead to the oxidative decomposition that can easily occur at high reaction temperature. So it will limit the formation of your uh, polymer. So these are three ways that you can do to achieve high molecular weight polymer in a polymerization. Okay, I think that's all for state growth polymerization topics. I hope you understand and watch all the videos that have been prepared for you. So don't forget to do the exercise. And for this uh, topic, okay, we have exercise which is gel point exercise that have been uploaded in the separate document. So I hope you do all these exercise, and we will discuss this exercise during our face-to-face class later. So happy holiday to all of you. Please take care of yourself and enjoy your Hari Raya, and see you again soon. Bye.